Okay, in 510, you are going to be writing your own integrals. So that's going to be the challenge today, is writing your own. Once you get the integral done, I think you'll know exactly what to do because you're good at integrating. So things to remember before we get started. When you are doing an integral, what you're actually doing is you're multiplying, remember, the x and the y together. So y is getting multiplied by the x when you do integration. Remember, derivative is dividing, integrating is multiplying. Basically giving you the area under the curve most of the time. And the other thing that's going to come up in this section is back to Riemann sums. Remember, a Riemann sum approximates the area under the curve using rectangles. And remember, the limits on the Riemann sum equaled our integral, the actual exact value, but Riemann sum was the approximate. So I'm just going to take you through the first example in the homework section here, because I think it's a little more straightforward. And then that's going to be it, but it's a long example. So I'm just going to kind of slide the book back and forth so you can see. I'm not going to make you write everything down on this example because it's right in your book. So if you wanted your book open, you could have it open to page 227 if you have it with you. If not, it's not a big deal, but it's number 1. So first thing, it's giving us a situation, a velocity equation. Suppose you take a long trip, you're impatient to arrive at your destination, so you gradually let your velocity increase according to this equation. So here's your velocity equation. Your velocity is at 55 miles per hour plus your impatient 12 times t to the 0.6. So first thing we want to do is graph this velocity equation. Draw the narrow vertical strip with width dt. This is all right in the directions here. Then show a sample point TV on the graph within the strip. Okay, if you were on your own, you'd probably say, what is that even saying? So draw a narrow vertical strip of width dt. Show a sample point TV on the graph within the strip. All right, so first thing we need is the graph. And the graph is actually in the book. And here's what the graph looks like. At time 0, we're actually at our 55 miles an hour, and then we increase our velocity here like this. Okay, so on here they wanted me to pick a narrow vertical strip. Well, that just means, just like it says, a narrow vertical strip. Call the width of it dt. Oh, because our time was in hours and our velocity is in miles per hour. Forgot that. Okay, so back to the part A. Draw a narrow vertical strip. Show a sample point TV on the graph within the strip. So anywhere in here they want you to pick a t value. It doesn't matter where. You can put it right in the middle. You can put it on an edge. It doesn't matter. I want to stick it right in the middle. So I'm going to pick this to be my t. It wants me to show this point. So I have a horizontal value of t. It's our x value. And then that has a corresponding velocity. I don't know what it is. I'll just call it v, some velocity. So I've shown my point within the strip. Part A is done. Part B says the distance you travel. Remember, we've got a velocity and time graph. If I want to know my distance traveled, I've got to multiply velocity times time. And what they're telling me, it says the distance you go in time dt. So my distance traveled on this part of the graph here, and it tells me is equal to the value of v at the sample point times dt. Write an equation for dy, the number of miles you go. So what we're actually doing is just multiplying velocity times time or we're actually finding the area of this rectangle here. If I pretend that that's a rectangle, my velocity is this equation. So in place of velocity, I'm going to put what my velocity is. 55 plus 12t to the 0.6. That's my velocity. My time is this distance across here, which I've defined as dt. It's all the way through this whole strip. And they're calling that my distance traveled. And the distance traveled, they're calling dy. So, just replacing the height of my rectangle with my velocity, because that's what it is, and then my width of my rectangle is dt. Okay, part C says write a Riemann sum for your approximate displacement as distance between A and B. So what they did in the book was they just made it a little bit wider. A to B. Remember, a Riemann sum just chunks this all up into all of these same size rectangles all the way through here and adds up all of the areas. And the symbol for a Riemann is that sigma, which says add up from A to B all of the rectangles. And the rectangles all have the velocity as the height and this dt as the width. So it's this equation that I wrote right here. So 55 plus 12 t to the 0.6 dt. So just taking this equation for one rectangle, turning it into a Riemann sum, which says add up all of those rectangles all the way through this interval from A to B. Part D says write an expression for the exact displacement you get by adding up all the dy's and taking the limit as dt approaches 0. When you see the word exact, that just means turn this Riemann sum into an integral from A to B of 55 plus 12t to the 0.6 dt. This section is just trying to make that connection that we did in the last section where the limit of the Riemann sums is equal to the integral. So is there any difference here? Not much. We're just replacing the Riemann sum with the integral sign. Okay, this is an exact value. This one's an approximate. Now part E says, how far did you travel in the first hour? So we want distance traveled in the first hour. Well, this is where you've got to interpret. Well, what part of the graph is that in the first hour? Because I want the area of that section of the graph. Well, the first hour would be from time 0 to time 1 hour. So 0, so at the beginning of the graph. So it would be from 0 to wherever 1 hits here. I want that area from 0 to 1. So all I've got to do is use my integral that we wrote here in part D and put my values on the boundaries here. So I want the integral from 0 to 1 of that equation that I wrote all on my own. And once it's like this, I think you're going to see there's not much struggle here. It's in understanding what the book's asking. It's kind of wordy, and I think that'll be the issue. But once you figure out what they're saying, it's pretty easy to do. So doing the integrating, remember there's no power here other than a 1, so throw away the parentheses, do each term separate, and it's in terms of t's instead of x's. So this goes to 55t. Here, the 12 is a multiplier, I carry it. I'm going to add 1 to this exponent, and then multiply by its reciprocal, which is 1 over 1.6. We'll just divide this by 1.6. And then I'm going to evaluate this thing from 0 to 1. And I think I already have it in here. Y equals, yes. So if I go to the table, have it start at 1. So at 1 hour, 62.5. Minus when I put in 0, Um, 55. Oh, I have the wrong equation in here. Dang it. 55x plus, okay, I'm try that again. Yeah. Okay, minus 0. Okay, now I got it right. So what that means is I traveled 62.5 miles in that first hour. Okay, now the question changes to how far did you travel in the second hour? So in the second hour, distance traveled. Well, think about second hour. You got to decide, well, what part of the graph is that for my second hour of my trip? Well, that's the integral from 1 to 2. 1 to 2 of that exact same function. So I'm just going to, no, I already did the integrating. I'll have to do it again and just change these boundaries to 1 to 2. So I'm going to integrate from 1 to 2. So I've got the table here all set to go. So at 2, it was 132.7 will go. Minus at 1, it was 62.5. So in the second hour alone, I traveled 132.7 minus 62.5, 70.2 miles in the second hour. So overall, in the first 2 hours, I traveled 132.7 miles. And then it's the last part of this question says, show that the property of the sum of two integrals with the same integrand applies. So what they're saying is, would you get the same answer if you evaluated from 0 to 2 as you would get from adding those two together? And we know that that's true. We saw that in the other section. But doing the integrating from 0 to 2, I was going to switch it to show that I'm integrating this same equation. The 2 came out 132.7. The 0 came out 0, so I get the 132.7, which does equal what I get if I add my two previous answers together. Sorry. So I plugged in the 2. I already had these answers, 132.7. Subtract the 0, that came out 0. And if I look, that does equal the two values that I got added together. Okay, and then the last question here says, I'll squeeze it in at the bottom here, F. Says, how fast were you going at the end of the second hour? How fast at the end of the second hour? Okay, first of all, how fast? That's velocity. Well, I started with a velocity equation. All I've got to do is plug in a time and I'll know my velocity. Well, what time is it if I'm at the end of the second hour? The end of the second hour means I'm at the start of the third hour. So I want to plug in time equals 3 to see what my velocity is. And I put that back in the original velocity equation, not this antiderivative equation that we found. So plugging, so again, that was not difficult. It was just knowing which equation to go to and what value am I putting in. So I want the velocity at 3 would be 55 plus 12 times 3 raised to the 0.6. And then whatever that comes out. And that'll be miles per hour. Guess I can type that in real quick.